Professor Yunhei,
Okay,
you can start,
yeah, I,
please.
I, I think we can start. So, hello everyone. Welcome to take part in today's European Non-Associative Algebra seminar. Today, Professor Zohreh Ravanpak will deliver us a talk. Uh, she is currently a visiting scientist at the Max Planck Institute of Mathematics in Bonn, and she will begin a new position as a research fellow at Nanyang Technology University in Singapore in the next academic semester. And today, the title of the talk is NIL Bialgebras, Structures, Hierarchies, and Applications in Integrable Systems. Let's welcome.
Thank you very much for the introduction, and thanks the organizer for the invitation. I'm going to talk about NL bialgebras. They are new algebraic concept that they are analogs to Poisson-Nijenhuis structures on manifolds. So that's why I would like to begin with a review of Poisson-Nijenhuis structures on manifold. And I will try to make definitions brief, but don't hesitate to ask me questions. So let me start with the definition of Poisson structure, which is a bivector pi on a manifold for which the scatter Nijenhuis of Poisson structure with itself is 0. Given a bivector, we can have this sharp map, which is a bundle vector morphisms. And then via this map, we can dualize Lie brackets of vector fields on Tm to a bracket on defined on differential form, the space of differential forms of M. So since this is a Poisson bivector, we get this bracket defines really a Lie bracket, and this sharp map is a Lie algebra morphisms. The other structure is Nijenhuis structure, which is a 1-1 tensor field on M, for which the Fourier Nijenhuis bracket of M with itself is 0. We call this condition Nijenhuis torsion, and if a linear map is torsion-free, then we call it Nijenhuis structure on the manifold. So via this map N, we can deform Lie bracket of vector fields on Tm to a bracket defined by N, which we call it deform bracket. And if N is torsion-free, then this defines a Lie bracket. And in this case, this N is a Lie algebra morphism between these two brackets. Now, having a Poisson structure and a Nijenhuis structure, we can construct a Poisson-Nijenhuis structures if they satisfy the compatibility conditions, two compatibility conditions. The second one is called concomitant of pi and n, and it shows the interaction between pi and n, and what compatibility condition says to us can be captured into this diagram. So consider this diagram. This is a composition of map N and pi sharp and N transpose, which is transpose of N on T star M. Also, we can have a map in the middle, which can be obtained by composition of these linear maps. The first condition tells us that this diagram is commutative. So the map between is simplified to n pi sharp. And actually, the first shows that we have a new bivector. NP defines a new bivector. Second condition. What tells us second condition? So here in the top, by pi sharp, we can dualize a the Lie bracket of vector fields to a Lie bracket which shows by sub pi. And then we can dualize it via n transpose, and we get a bracket here. We show it by the first one, which is n transpose pi. So the second, we can first deform a Lie bracket and then dualize it. So dualization of deformation. We show it by the bracket in the middle. That's the third one. Having a bivector, we can dualize a bracket, and then we get a new bracket here, which I showed it by brackets sub n pi. So the second condition tells us that all these three are the same. And so the dualization and deformation is equal to deformation of the dualization. Moreover, we have this implication of this compatibility. Says that this bracket defined by new bivector is a Lie bracket. So indeed, it is a Poisson bivector, and moreover, it is compatible with the initial Poisson structures. Another thing that we get here is that all these map are morphisms of Lie algebras with respect to corresponding bracket. And another thing is that n transpose is Nijenhuis structures of on T star m. So all these three implies from these two compatibility conditions. So we have a nice picture of Lie algebra morphisms. So the idea is that having a Poisson structure and Nijenhuis structure, we can produce a new Poisson bivector. But the main feature here is that having PN structures, we have a hierarchy of structures. So it's well known that if we have a Nijenhuis structures, then we have a hierarchy of Nijenhuis structure, meaning that any power of n is Nijenhuis with respect to any of deformed Lie bracket. So using this condition for Nijenhuis structure, we can define a hierarchy of compatible Poisson structure, which characterized by pi sharp and k pi sharp. So this is iterated by n of any power. So in PN structure, when we have this compatibility condition, we have a nice whole hierarchy of structures, a hierarchy of Nijenhuis on Tm, a hierarchy of n transpose on T star m, a hierarchy of concomitant, and a hierarchy of compatible Poisson structures. So the goal is that to explore these constructions analogs to PN structures on Lie bialgebra. And our motivation comes from the importance of PN structures in bihamiltonian system, because they produce compatible Poisson structures, and they are algebraic framework to introduce to construct bihamiltonian system, and in certain conditions they are integral. So my goal is to have such a construction here on a Lie bialgebra. So using that, I produce compatible Lie bialgebra. And since they are one-to-one correspondence with compatible Poisson Lie groups, and both are important in bihamiltonian system, so this construction can be very interesting. So let's have a brief review of Lie bialgebra. So the main ingredient for this work is a Lie bialgebra, which is a pair of Lie algebras compatible in the duality via a co-cycle. In the complex cohomology, which is defined by the second adjoint representation, which is extension of adjoint representation in the second exterior power of G. And we define a co-boundary operator, which takes any cochain here to k plus any k cochain to k plus 1 cochain, and this is the space of k cochain, which is linear map, K-linear map with the values in this space, second exterior power of G. And this co-boundary satisfied this condition can be defined by this condition, can be expressed the first time by adjoint representation and the second by Lie bracket.
Excuse me.
But we say that one.
Yeah. So I think
Yeah.
the K co-chains here, the CK. So do you require the skew symmetry condition?
Yes. Yes. Yeah. They are skew symmetric multilinear maps.
Yeah.
Yes.
Skew
Sorry.
symmetric.
Thank you. Yeah. A K cochain is called K cocycle if the coboundary of that is 0, and we call it K coboundary if there exists a cochain of 1 less degree, such that we can write that cocycle in terms of the coboundary of that element. So here for us, 1 cocycles are important. We say a 1 cocycle defines a Lie algebra if the dual map to that cocycle defines a Lie bracket on G star. And then the cocycle and that bracket talk together via this relation. So sometimes we show a Lie algebra by a Lie algebra with a cocycle delta, and sometimes we show it by the pair of Lie algebras, G and G star. And G star, we mean that is just a dual of a1 cocycle, which is delta in this case, I mean, in our notation. So then we have coboundary Lie algebra if the associated cocycle is coboundary. This is by definition. There is a sufficient condition to have coboundary Lie algebras by using the solutions of classical Yang-Meister equation. So R is a solution of, this is for skew symmetric. We say that R is a solution of this equation. This is the equation. If satisfied, this is the algebraic Nijenhuis of R with itself, which is defined by this. If this is a 0, then we say it's a solution of this equation, and the solution are called R matrix. When we have a solution of classical Yang-Meister equation, that the coboundary of that obviously is cocycle, because the coboundary of coboundary is 1 cocycle. So the only thing we need is that the dual of this cocycle defines a Lie bracket on G star, and it is guaranteed by the fact that R is R matrix. So having R matrix, we have coboundary Lie algebras. And for R matrix, the sharp map is Lie algebra morphism between these two Lie bracket up to sign. So any question up to now? The second ingredient in this board are Nijenhuis operator, which we take it a linear map. So our ambient space is a Lie algebra. We take this N directly on the Lie algebra instead of tangent bundle of the ambient space, things that usually people do. So we take N directly on G, and then we define Nijenhuis torsion. As I mentioned in the beginning, we define a deformed bracket. And if this N is torsion-free, then we have a Nijenhuis operator. What I want to mention here is that there are linear operator on G for which this deformed bracket is a Lie bracket, but they are not torsion-free. So actually, the Nijenhuis torsion for them is a 2 cocycle in the cohomology complex defined by adjoint representation. In this case, we call it almost Nijenhuis. So that these are bigger than Nijenhuis structures. I would like also to mention about some notation that we will see during the talk. So we can write the adjoint representation of deformed Lie algebra in terms of this commutator of linear map adjoint representation of the initial Lie algebra and n plus an extra term. For simplicity, I write this commutator by at underline. So whenever we see at underline, I mean the commutator of this two-layer map. And these here are just the quadjoint part in terms of quadjoint representation and n transpose. So in this, with this notation, for example, we can simplify the Nijenhuis torsion-free condition to this. And we have it in terms of quadjoint representation. So it helps us to simplify the computations. So a stricter condition on linear operator on G is that that commutator is zero. So if that commutator is zero for an operator n, we call it ad equivariance, or simply equivariance. So it's obvious that ad equivariant operator are Nijenhuis operator. So these are stronger than Nijenhuis operator. We can similarly define such a add star equivariant on G star, but we should be careful because this add star is not quadjoint representation, it's adjoint representation associated with this Lie algebra on dual space. So if this G star is dual algebra of a Lie algebra, then there is an equivalent condition for n transpose to be ad star equivalent, which can be written in terms of the cocycle n transpose and n. Does that make sense? Does it make sense? So this is the equation that we get for this n transpose, and we use it also. This observation we use during our proofs. So that was about Nijenhuis structures. I would like also to mention about notation on cocycles. Saying that having a linear map on G, we can extend it to a linear map on K power of G. And it's just to distribute the transpose of that initial map to each component. So this notation we use, and it satisfies this equality, saying that the uta of commutator is commutator of utas up to sign. For example, in our case, we have a linear map on G, we have a cocycle, then uta n transpose is just to distribute n transpose to each one. Or we can simplify the condition for delta to be one cocycle in terms of this uta. So I'm done with the definition, basic definitions. Suppose that we have a Lie algebra and we have a Nijenhuis operator, and we want to say how they interact with each other in order to produce new Lie algebra. So considering the top of this diagram, we have a Lie algebra, so a pair of Lie algebras. We have three ways of deformation. Either we can deform the first Lie algebra by means of n, and we say one cochain on deformed Lie algebra, or we can deform a dual Lie algebra by means of n transpose. We get another pair of Lie algebras. So here, to be sure that the deformation by n transpose defines a Lie bracket, we impose the condition for n transpose to be almost Nijenhuis. And we call it the formation of one cocycle and the algebra by means of N transpose. Or we can, the next step is that we have double deformations by means of N transpose in this step. So how they characterize? Here, for the left-hand side, you see that delta is just defined by the dual map to cocycle. So since the dual map here is the same, it means that delta and delta up n, this is the just notation, we mean that delta is considered in the deformed algebra. They satisfy the same definition condition, but with respect to different algebras. Here, in the right-hand side, for the deformed cocycle, there is a way to write it explicitly in terms of delta n and n transpose, and also for the deformed cochain, double deformed. So here, now, our aim is to have this picture like this tree deformation defines newly by algebras. So we proved that the left-hand side defines Levi algebra if and only if the right-hand side defines a Levi algebra. So this is the initial result we have. This first one I just explained on the diagram. It means that the left-hand side is Levi algebra if and only if the right-hand side. And the double deformation is one cocycle if and only if satisfied in this condition. So this, I'm sorry. So this, do you have the whole screen? Sorry. Because it somehow, can you see the whole screen?
No, I don't think it's a full screen.
And now it's fine?
Now it's fine, but I don't know how to say, but at the side, there are some black. I don't know, it's the
Now it's
problem.
fine.
Yeah, but on the bottom, there are still a gray box. Yes, so
Yeah, from the
now,
beginning it was like that.
now it's okay. Yeah, I think now it's okay. So just now I thought it's oh, now the full screen is a gray box.
Right.
Okay,
Just a
so it's not
moment.
my problem. So just now I thought it's the problem of my computer. It seems not.
Uh-huh.
Now we lost
Where
the
it
slides.
goes.
Yeah.
I'm sorry, just a moment. I don't know where it goes. Maybe I share it again. Where? Ah, my gosh, that's here. Yes? I shared it already. Any idea what can I do? My gosh.
Maybe you want to stop sharing and reshare.
Now it's fine. I think, yeah. Is it fine? You have?
Now we can see your slides, but at the bottom there is a gray box. Now yeah, at the bottom. Yeah.
Bottom is the gray box, but it's not something that I can.
Oh, it's bigger.
I think now it's fine. Now it's
Oh,
fine.
now it's fine. Now it's fine.
Yeah,
Okay.
yeah.
Yeah.
Now it's fine. Okay.
Please continue. Yeah.
Yeah, yeah. I don't touch it anymore. So that, yeah, let's back to the diagram, and we want to have these all pairs of Lie algebras to form Lie bialgebras. And I say that the right-hand side is Lie bialgebra provided the other side. And here in the deformed, the double deformed, we define concomitant of delta and the concomitant, if the concomitant vanishes, we assure that the deformed cochain, the double deformed cochain is a one cocycle. So that's now we can define our desired structures. We say that if we have a Lie bialgebra and if we have a Nijenhuis structures such that the transpose is almost, then we have a weak NL bialgebra if the following condition holds. So this resembles a kind of compatibility condition in the PM structures. And in case this N transpose is torsion-free, we call it NL bialgebras. So this is the definition. Any question up to now? Okay. So for covariant case, the situation is much easier because when we have an R matrix and when we have a Nijenhuis operator, then we have a new bivector defined by N after R sharp. And then this pair defines a covariant NL bialgebra if and only if satisfy these two conditions. You see that here concomitant is simpler than before. So it's just in terms of the commutators. So the picture that we can have for covariant is captured in this diagram. So in the covariant case, having our matrix and Nijenhuis operator, we get a new, with that two compatibility condition, we get a new R matrix. This is the ideal. Producing new structures, iterated by Nijenhuis structures. And then we get that all of these pairs defines Lie bialgebras. And moreover, N transpose is Nijenhuis structure. So in the covariant case, we do not need to impose this condition for N transpose. It implies directly from the compatibility condition. And the bracket defined by NR, which is a new Lie bracket, is just the same as the bracket which can be deformed by N transpose from the initial one here. So these are also important, which kind of they are the same of PM structures. So the point here in our construction, to define hierarchy, we have three hierarchies. We have hierarchy, so to have a hierarchy of compatible Lie bialgebras, we need to define the hierarchy of structures we are dealing with. First, a hierarchy of Nijenhuis structures that I've already talked about it. Second, hierarchy of adjoint representation means that the adjoint representation in each step of hierarchy can be expressed in terms of adjoint representation in the previous step. So they are iterated by, and also the hierarchy of cochains, because the condition for one cocycle need to be checked in each step. So having this hierarchy, we are looking to have a whole hierarchy of compatible Lie bialgebras. So which you can see it in this picture. So started with a Lie bialgebras, with a Lie bialgebra and a Nijenhuis operator. We have deformations via N transpose. We have double deformations, and each step we can deform it by N. So to have the whole of this picture, to define compatible Lie bialgebras, we need a hierarchy of algebras in the left-hand side, which is guaranteed by having a Nijenhuis structure and G, and having hierarchy of dual on dual Lie algebra, which is currentized if we suppose that N transpose is Nijenhuis. The other thing is that we need to have this middle, the pair in the middle defines Lie algebras. First of all, we prove that every three pairs in a row defines a Lie algebra, provided the other one defines a Lie algebra. So, second, the concomitant happened in this part of this diagram where a double deformation happens. We want to have a hierarchy of concomitant to be one-ish also. So using this result on hierarchy, the first one I just explained on the diagram means that on the row, we need just to prove that one of those is one cocycle, the other implies directly. And for co-boundary case, it's important that for the co-boundary case, if we have a hierarchy in the middle, there we have a hierarchy on each step. It's one-ish there. That we have a hierarchy of concomitant. If CRN is 0, and then for any degree is 0. For the hierarchy, for co-boundary bialgebras, this hierarchy is well defined, so no problem. But in case non-co-boundary and bialgebras, we need more consideration. So this is the concomitant in the hierarchy, and we need this to be one-ishes in order to have all this pair in the middle defines Lie algebra. And it happens if either this at underline is 0, so it's obvious. In this case, by the definition of adequavariant that I mentioned in the beginning, means that N should be adequavariant. So it's a stricter condition that we need to impose in order to have the whole hierarchy. Either the whole should be 0, and the whole should be to have the whole 0, we need to impose this condition. So it's equivalent with this condition. And this condition, if you remember, it's equivalent to the condition that N transpose is Abel-Star equivariant. So these all lead us to the main theorem of this work, which says that having an NL bialgebra, there exists a whole hierarchy of compatible bialgebras if and only if the following satisfies. If and only if N is adequavariant, or N transpose is Abel-Star equivariant, or delta is a co-boundary cocycle. So having these three, then we have the whole hierarchy of Lie algebras. So this is important having this hierarchy. However, imposing N to be equivariant is a strong condition. But since my goal was to have the whole hierarchy, I was looking for a condition to have this, and this is complicated in bialgebras because in Poisson structures, this when N is Nijenhuis structures, we have automatically N transpose is Nijenhuis out of those two compatibility conditions. But in Lie bialgebras, it is more complicated and need more considerations. Here, if there is any question up to now, I'll be happy. Otherwise, I go for the example. Oh. So here we have example of a weak NL bialgebra. So we see that this pair of delta and N defines a one cocycle, and Nijenhuis structures on this Lie algebra, which is which is known by book Lie algebra, and they are compatible. I mean that this pair defines an L bialgebra. I will explain it. So the the transpose of the cocycle defines a Lie algebra on G star, and that Lie algebra is just SO3. Moreover, the transpose of this dual map by means of N transpose defines a Lie bracket, a new bracket, which we will see it's also a Lie bracket on G star, and that is just Lie algebra of SL2R. So our data is a delta and N on a Lie algebra. With this data, we have this picture of compatible Lie bialgebras. So how? This is the first one. Okay, with that data, we prove that the delta is also a cocycle in the deformed Lie algebra with respect to the deformed Lie bracket. And as I mentioned in the beginning, we proved that this is Lie bialgebra if and only if this is Lie algebra. And since the delta here we proved it, means that we have also here a Lie bialgebra. With those data, we showed that the concomitant of delta and N is 0. So means that the double deformation is also a Lie bialgebra. Since N transpose in this example is not actually a Nijenhuis structures, it's not Nijenhuis torsion free, but N transpose deformed the bracket to a Lie bracket. It means that it's almost here. So here it's well defined. I mean that we are dealing with a pair of Lie algebras. Note that here we have another step here. We can go further because in this example, the deformation by N2 and N transpose 2 defines also a Lie bracket. However, it's not necessary because I mean, it's not obvious when we have an almost Nijenhuis. It's not obvious if we have Nijenhuis, the bracket, the Lie bracket in hierarchy. So this is one is to check in each step. And this is the whole picture of this example that we can have all compatible Lie bialgebras. But why it's important? Look at the right-hand side of this diagram on the top. If you remember, we started with a G, which was book Lie algebra. Dual Lie algebra was SO3. And here in the corner in the right, this G star is SL2. So consider these compatible Lie bialgebras, and I will show you that here is a kind of where a well-known dynamical system happened. So consider these two Lie bialgebras in that diagram, as I explained. And think of G as a vector space, which can be considered as a Lie group with addition. And then associated with any algebra in Rn, we have linear Poisson structures. So then we can consider these two linear Poisson structure associated to SO3 and SL2R on an abelian Lie group. And then with respect to these two Hamiltonian functions, we see that the dynamics defined by these two compatible Poisson structures coincide. And this is an integrable system. Actually, it's also completely integrable. It's equivalent to a particular case of SO3 Euler-top, which is well known by Hamiltonian system. So it means that the weak NL bialgebra that we had, it's an algebraic framework for this Euler-top system. So what we can do more in this area? So here I introduced NL bialgebra, which constructed by a pair of delta and n on a Lie algebra. And I showed that how they define in a certain condition compatible Lie algebras. And also in the example, I explained how they can define by Hamiltonian system on abelian settings, considering G as abelian Lie group. Actually, in our last work, we showed a process which can get another Hamiltonian setting here in an abelian setting. So how? We integrate Lie algebra G to a Lie group, and then under this deformation, which is eta deformation, so don't please mix it with the deformation during the type. It is another story, which eta is the deformation parameter, means that when eta goes to 0, we get abelian setting. And then we construct here in right-hand side a bi-Hamiltonian system on this Lie group. So compatible by algebra, and this bi-Hamiltonian system is defined on this compatible Poisson Lie group, which was obtained by integration of compatibility by algebra. So this is the structure that we had in our previous work, and in the right-hand side, we have the deformation, the parameter eta appears, and when eta vanishes, goes to 0, then we kind of get the any counterpart in the left-hand side. So if eta goes 0, G go to G, compatible Poisson structure gives to the linear, and also the Hamiltonian system or Hamilton. So the aim is that actually this construction helped me to define such a structure, because I saw that there are some bi-Hamiltonian systems which cannot be explained via the classical Poisson, the traditional Poisson Nijenhuis structures on manifold, and I could see that there should be a relationship, or there should be another setting we can define such a bi-Hamiltonian system. So in a research in progress, I am trying to integrate such an object. So obviously that can be Lie algebra can be integrated to pi, but it's not obvious for me at the moment and how they will talk together to be compatible, to define compatible Poisson Lie groups. And I am not sure, I didn't mention Poisson Lie groups, but they are Poisson structure which are compatible with group multiplication. So that was all I wanted to say. I'm sorry that problem happened during my talk, and maybe some of you were interrupted. And thank you for your attention.
Okay, so thank you for your next talk. Are there any questions or comments? So maybe first I ask a question. So could you move back one page? So just the page 25. So there you mentioned the compatible Lie algebras. So could you roughly explain the definition?
I should have mentioned it in the beginning. Yeah, they are when two Lie algebras are compatible. If Lie algebra of those are compatible, and all Lie algebras are compatible together. And compatibility of Lie algebras means that the sum defines again a Lie algebra.
Okay, so any linear combination is again a Lie algebra. Okay.
Yeah.
Mm. Yeah, because we have a paper study compatible Lie algebra. It consists of two Lie algebra structures, such that any linear combination is again a Lie algebra structure. Yeah.
Yeah. Actually, in this picture, otherwise we will not get compatible Poisson Lie group.
Okay.
This needs, I mean, compatibility bialgebras are one-to-one correspondence with compatible Poisson groups. This is also, and the compatibility of Poisson structures, two Poisson structures are compatible if the scatter-Nijenhuis of those is 0. And it means that again the sum of those are 0. The sum of those defines a new Poisson structure. Multiplicative in this case, yeah. Yeah, I should have mentioned it. That this compatibility usually say that if the two structures are compatible, if the sum of those defines the same structure.
Mhm.
Mhm.
Okay, so another question is, you have a very big diagram. So I'm still curious about so the deformed Lie bracket, the deformed algebra by the Nijenhuis operator n, and the deformed algebra structure on G star by n star by the transpose of n. So for those two algebra structures, are they Lie algebra?
This picture, maybe I show it here. Yeah.
Yeah. Yes.
And the question is that if these are, can you see that my mouse is moving?
Yeah.
Okay.
I can see it.
Yeah.
Yes.
So this is this condition here we impose. I mean, for NL bialgebras, that here if we have a delta, we impose delta should be a cocycle also in this cohomology, in the deformed cohomology. And when we impose the condition here, so we have a Lie algebra here.
Yeah.
And having a Lie algebra in the left shows that the right one also is Lie algebra.
Okay.
This is proved.
Yeah.
This
And
is
then
proved. And concomitant happened in the middle.
yes, the second middle one. So my question is, this guy is this guy a Lie algebra?
Which one?
Just I mean the second line. Yeah. Yes, exactly.
This is concomitant. Yeah, we say that, we say a pair of delta and n is NL bialgebra if is Lie bialgebra and this is Lie bialgebra. I mean, the concomitant should be one-ish.
Okay.
And this is kind of resemble the second compatibility condition when we say that dualization of the formation should be the same as the formation of dualization. Yeah. The equality of bracket here defines in the feature of being cocycle.
Okay.
I mean, the deformation. However, I do not have dualization here. Maybe this n transpose one can say this is dualization, but because it happens in dual space, but since I deform it by n transpose, I prefer to kind of keep the deformation.
Okay.
And here the double deformation is concomitant, which we impose the condition to be 0.
Okay. So this double deformation is still Lie algebra. So could you show me the condition again?
Yeah, sure. It's concomitant. It's for here. Yeah. It's very kind of not similar, but because for the concomitant, there also we have this commutator between Lie derivative of forms and n transpose, and here we have this between adjoint representation and if you see it.
So this condition is stronger than your definition of NL algebra, right? Is this the definition of NL algebra or stronger than the definition of NL algebra?
No, it's one of those compatibility conditions. The definition of NL bialgebra is that if delta n satisfies these two conditions. first says that the left-hand side is the bialgebra. The second says that in the middle.
So you mean for a weak NL bialgebra. So for a weak NL bialgebra, then the double deformed algebra is again a bialgebra.
Now, what I define here, I say that delta and n defines an NL bialgebra if we have this diagram compatibly bialgebras. And when it happens, if we have those two compatibility conditions, you can see it in the example, for example. Maybe it's better. In the example, I just take the algebra, I put delta, I put n, and I claim this defines we can NL bialgebra. And why? If I have this picture of these compatible bialgebras, the bialgebras, yeah. And it happens with the data that I have. I just need to show that this delta that I have in the previous slide is co-cycle with respect to the deformed cohomology, which is, in this example, this needs to be checked. And then according to the theory or lemma, we get the right-hand side also. The bialgebra, in the certain example, I show that the concomitant is 0. You see, this is the condition that delta and n need to be satisfying.
Okay. Yeah. Okay.
Was that clear?
Okay. So I will write to you by email. Okay.
But it happens in the Poisson-Nijenhuis structures. Look at the diagram we have in here. So exactly here, we impose the condition in order these three to be the same. This is a condition. We put it here in concomitant. Look.
Yeah, but I just want a statement. So could I say for a weak NL bialgebra, then the double deformed two algebras. So the double deformed two algebras form a bialgebra. So that is my question.
Exactly.
Okay.
If it defines weak, exactly. For the weak bialgebra, we have the same.
Okay, that is my question.
Sorry. No, but because the type went fast, I wanted to mention it more clear now. And it was interrupted, that's why.
Okay, so now I understand. So what you have started is considered the Nijenhuis operator on the algebras. Yeah, and actually what we are discussing that our ongoing project is considered the bialgebra for Nijenhuis algebra. So I think that is the difference. Yeah. Okay. Yeah, we can discuss later. Yeah. Okay. So are there any other questions? Okay. So if no other question, let's thank Zohreh again. Thank you very much.
Thank you very much. Thank you.
Okay. So I think today we stop here. Bye bye, everyone. Bye bye.
Bye.